Hi and welcome Chemipedia chemistry classes for 12th standard. So in this video, I'm going to discuss about the different types of packing in the crystal, which comes in unit number 6 solid state lesson. So here we are going to discuss about the three different types of packing. That is packing in single dimension, two dimension, as well as in three dimension. Whereas under two-dimensional packing, we are going to see two different types, AA type packing and AB type packing. Whereas in three-dimensional packing, we are going to see three different packings, that is simple cubic, HCP, hexagonal close packing. The third one, CCP, cubic close packing, which is also nothing but FCC type of packing. So first let us see how the atoms are arranged in a single dimension. So single dimension arrangement, we have only one kind of arrangement, that is every atom is kept after other. So we can arrange atom one after other so that you get this kind of arrangement. Okay, so single dimension arrangement, we have only one kind of pattern. Okay, right. Now in single dimensional arrangement, you can see every atom is in contact with two other atoms, which means every atom is in contact with one atom before the another atom, so after it, isn't it? So that every atom is in contact with two other atoms, so that coordination number in case of single dimensional packing is about 2, because you know very well that coordination is number is nothing but the number of nearest neighbors, number of atoms to which an atom is in contact, number of nearest atom to which an atom is in contact with, isn't it? So this is information about single dimensional packing. Okay, the next type is nothing but two dimensional packing. Whereas as I said already, two dimensional packing, we are going to discuss two types. One is AA type, another one AB type. Okay, right. Now the first one, AA type, the one dimensional packing is repeated in two dimension. See, this is nothing but one dimensional packing, what we discussed earlier. Now this kind of packing is repeated in the other dimension also, two dimension, isn't it? So that because of that, we are getting more number of rows are generated, so which are identical to the first row. So all the rows are identical to the first row, isn't it? Now when you when you see spheres of any row, it align vertically as well as horizontally. So all the spheres are aligning vertically as well as horizontally, isn't it? Right. Now if you represent the first row as A type, even the other rows also identical to first row, isn't it? So every row can be represented as A. So this kind of packing is what we call it as AA type of packing. Okay, right. So other rows also identical to first row, so that it is called as AA type packing. Here the coordination number of atom is 4, because here in this type of packing, every atom is in contact with 4 other atoms. That is the reason coordination number is 4. That is, every atom is in contact with 2 atoms in the same row. So suppose if we consider this one, it is in contact with 2 atoms in the same row, one in the previous row, one in the next row, isn't it? So that is how it is in contact with 4 atoms, so that the coordination number of atom is 4. Okay, so this is about AA type of two-dimensional packing. The next one is nothing but AB type of packing. This also comes under two-dimensional packing. Okay, right. So first we have one-dimensional arrangement of atoms, first row, whereas the second row atoms are kept in the depression of first row. See, the second row is placed in the depression of first row. Suppose if we consider the first row as A type, the second row is different from the first row, because the second row elements or spheres are placed in the depression of first row, so that the second row only we can represent as B type. So now, okay, right. Then you can see the third row is placed in the depression of second row, which is looking identical to first row. These two rows are looking identical, isn't it? But third row also nothing but A type. Now the fourth row is placed in the depression of third row. You can see that fourth row is identical to second row, isn't it? Like second row, fourth row also represented as B type. So that this type of packing is what we call it as AB type of packing. So here the alternate rows are identical in nature. 1, 3, 5 rows and 2, 4, 6 rows are identical, isn't it? That's why this is so 1, 3, 5 are A type packing, 2, 4, 6 are B type packing. So this packing is called as AB type of packing. Okay, right. And here the coordination number of atom is about 6. So look at the diagram. Here this is the atom what I have selected. Now you can see this atom is in contact with 6 other atom, or it has 6 nearest neighbors, which means this atom is in contact with 2 atoms in the same row, 2 more in the previous row, 2 more in the next row. But totally it is in contact with 6 atoms together. That's why the coordination number of atom in AB type packing is about 6. Right. So this is about the 2 different types of 2-dimensional packing. Okay. So next let us discuss about the various types of 3-dimensional packing in crystal. So as I said already, we are going to discuss 3 different types of 3D packing here. Simple cubic, hexagonal close packing. The third one is cubic close packing. So first let us see about the nature of simple cubic. So this is a diagram for a simple cubic arrangement 3D packing in crystal. You can see here the AA type of 2-dimensional packing is repeated in 3 dimensions, isn't it? See, this is nothing but AA type of 2-dimensional packing. The spheres are arranged in 2 dimensions, isn't it? When this is repeated in another dimension also, when it is repeated in 3-dimensional pattern, then that type of packing is what we call it as simple cubic packing solver. Okay, right. Now spheres of every layer is placed exactly at the top of the spheres of previous layer. See, this is one layer, bottom layer. The second layer spheres are exactly sitting over the top of the first layer atoms, isn't it? Similarly, you can see the spheres of every layer is exactly fit over the top of the previous layer, isn't it? So that because of this, all the layers are looking identical. So all the layers are looking identical, as well as spheres in different layers. Spheres in different layers are aligned vertically as well as horizontally. So they are aligning vertically as well as horizontally, isn't it? Right. Now, so this is about the simple cubic arrangement. Okay, right. Here the coordination number of atom is 6, which means in simple cubic arrangement, so every atom is in contact with 6 other atoms. Okay, so just look at this. This is the atom what I have selected. So this is one layer. Okay, so for example, middle layer which, okay, then this is the atom which is in the upper layer, this is the atom in the lower layer. But now you can see the atom in the middle layer is in contact with 4 other atoms in the same layer, isn't it? Then one more atom in the upper layer and one more in the lower layer. So that the atom is in contact with totally 6 atoms, 4 in same, 1 in upper, 1 more in lower layer. So that is how the coordination number of atom in simple cubic arrangement is about 6. Okay, right. Then second type of 3D packing is nothing but HCP. What do you call it as hexagonal close packing? What do you call hexagonal close packing? Okay, so here we are going to see the way how the 3 different layers are formed. We are going to discuss together for HCP as well as CCP, because in HCP as well as CCP, the formation of first and second layers are similar, so identical, only they are differing in the third layer arrangement. Okay, right. Now the first, let us see how the first layer is formed in HCP as well as CCP. Okay, right. Now here the first layer is nothing but this kind, that is AB type of packing, AB type of 2-dimensional packing, in which the second row atoms are placed in the depression of first row, isn't it? Right. Then so suppose if you consider this as first row, this is second row, you can see this second row is fitting in the depression of first row, isn't it? Right. That's the first layer in HCP as well as CCP packing. Okay, right. Then so this let us consider as A type of layer. Okay, right. Then now we are moving to the formation of second layer. Then the second layer actually placed in the depression of first layer. This is first layer, so it has some depressions, isn't it? So voids. The second layer can be placed in the depression of first layer actually. Okay, right. Actually in the first layer you have 2 different types of voids, empty spaces. You have 2 different types of voids. One is considered as X type void, another one is called as Y type void. Suppose if we place the spheres of second layer in the X type void. Suppose second layer atoms are placed in the X type of void, then there a type of void called tetrahedral void is formed. So now see, so these are nothing but first layer. The colored sphere is nothing but second layer. You can see the second layer sphere is exactly fitting in the depression of first layer atom, isn't it? Right now, so here I have mentioned as T. T is nothing but a void which is formed between these four atoms. That is 3 in the lower layer, 1 in the upper layer. The type of void what you call it as tetrahedral void. Okay. So tetrahedral void is formed. The tetrahedral void is formed by placing the second layer atom in the depression of first layer. This tetrahedral void is formed between four spheres. There is 3 in the lower layer, 1 in the upper layer. That's what I said. 3 in the lower layer, 1 in the upper layer. Okay, right. Why is this called as tetrahedral void? This is called as tetrahedral void because when we join the centers of these four spheres, it gives a shape called tetrahedron shape. That is the reason why this void formed between these four spheres, 3 in lower and 1 in upper sphere, is called as tetrahedral void. Okay, right. Now, when we place second layer atom in the depression of first layer, the another type of void, Y type of void, isn't it? So that is partially covered by this atom. See this void, you can see this, there is another kind of void here. This is partially covered by this spheres of second layer, isn't it? Now this type of voids which are partially covered by spheres of second layer is called as octahedral void. Why this is called as octahedral void? Actually this void is formed between 6 atoms. That is 3 in the lower layer, 3 in the upper layer. You can see 3 spheres in the lower layer, 3 more in the upper layer. Actually this void is formed between this totally 6 spheres, isn't it? Right. So the void which is formed between 6 spheres is called as octahedral void. The reason is when we join the centers of these 6 spheres, there is 3 in the lower and 3 in the upper sphere, we get a shape like this. Okay, octahedral shape. That is the reason why these kind of voids are called as octahedral voids. Okay, the void Y partially covered by spheres of second layer. It is formed between 6 spheres, 3 in lower and 3 in upper layer. So I have drawn the diagram for tetrahedral and octahedral voids. Okay, 3 lower layer atoms, upper layer atom. So this forms tetrahedral void. 3 spheres in the lower layer, 3 in the upper layer. So here an octahedral void is formed. Okay, so I have given a diagram for the representation of tetrahedral and octahedral voids. Okay, right. Let us see the formation of third layer in HCP as well as CCP structure. Okay, so this is nothing but the arrangement in HCP case. This is the first layer. It's nothing but AB type of 2-dimensional arrangement. Then this is the second layer. The first layer we represent as A type. The second layer atoms are placed in the void X of first layer. So we call it as B type. Now this is nothing but third layer. Now you can see the third layer is exactly identical to the first layer, isn't it? So that third layer also considered as a type layer, isn't it? So that in HCP packing we have A type layer first followed by B type, then again A type. So that HCP arrangement we call it as ABA type of packing. What do you call? ABA type of packing. Okay, so this is the diagrammatic representation of HCP type of packing. Okay, right. Now let us see the formation of third layer in CCP type of packing. Okay, right. So now look at this. In HCP, the third layer is identical to first layer. So first and third layers are identical. So that arrangement is called AB type. That's what I discussed, isn't it? Whereas in CCP type of packing, the third layer formed is over the second layer. That's third layer which is formed over second layer is exactly fitting into the octahedral voids of first layer. See, first layer AB type of 2D packing. Second layer atoms are placed in the tetrahedral voids. Now the third layer atoms are exactly fitting over the octahedral voids of first layer. Now when you look at the third layer, it is looking different from first and second layer. So first layer if you consider as A type, second layer as B type, the third layer is different from the first and second layer, so that it can be denoted as C type of packing. Okay, so this is first layer, this is second layer. Second layer you have one type of arrangement, isn't it? Look at this third layer. It is like 1 2 type, isn't it? So at the front you have one atom, back la 2 atom, whereas here B type layer la second layer la front la 2 back la 1 irukku. Now there is a difference between the second and third layer, isn't it? So first layer if you represent as A, second B, then third one which is different from first and second, if you represent as C, then this kind of packing, CCP packing, we call it as ABC type of packing. What do you call? ABC type of arrangement. Okay, right. So this is about the two different 3D packing, that is HCP and CCP packing, along with the simple cubic arrangement, isn't it? Right. Now in HCP as well as CCP, the coordination number is about 12, because in both the cases every atom is having 12 nearest neighbors, so that in both the cases the coordination number will be coming around 12. But now let me tell about CCP packing. Okay, right. Now so this is the atom. Let us consider this atom. Now you can see it is in contact with 6 in the same layer, isn't it? Now this will be placed over this. So here you have 3 atoms, but this center atom will be contact with even this 3 also. About 6 plus 3, 9. Then below this layer you may have C type of layer, that also consists of 3 atoms. So totally this central atom is in contact with 6 in same layer, 3 in the upper layer, 3 more in the lower layer. But totally it is in contact with 12 atoms. That's the reason why the coordination number of atom in CCP packing is 12. Okay, even in case of HCP also, the coordination number will be about 12. Okay, right. So just have a look at the HCP diagram. Okay, right. So this is AB type diagram, isn't it? Suppose this is B layer, A layer. Above this you may have A layer, B layer, isn't it? So now let us consider this atom. Below layer it is in contact with 3. Same layer with 6 atoms. The other layer also nothing but B type, which consists of 3. Totally this atom is contact with 6 in same layer, 3 in lower layer, 3 in upper layer. Totally this also in contact with 12 atoms, isn't it? So that is the reason why in HCP packing also the coordination number is about 12. Okay, right. So that's all about the different types of packing what we have in the crystal lattice. Okay, right. Thank you.